Hi everyone, thanks for coming to my talk on assessing the accuracy and precision of portable X-ray measurements of potentially toxic trace elements in field soils. This is a collaborative project with the University of Massachusetts Amherst, my institution, and the University of Vermont. And this is funded by the NRCS under the USDA, under their Soil Science Collaborative Research Program. So many thank yous for funding to pursue this project. So first off, what is portable X-ray fluorescence? Essentially, it is a rapid way to assess elements in soils. Really quickly, in 30 seconds to a minute, you can generate total elemental concentrations for a dozen or so elements. And because of that, it's quite advantageous because you can measure hundreds of soil and rock samples within a single day. So there's a lot of advantages over traditional ICP-MS methods. But there are several drawbacks because it can only measure elements that are heavier than sodium. There's also some software limitations because they're oftentimes proprietary, and the models and quantitative methodology used is not always accessible to users to alter and use different standards. There's also some issues with total elemental concentration data because if you're thinking about crops or plants or trees, that not all those elements are readily accessible for uptake, and also in uptake into biological systems like humans in groundwater or fish, for example. And then lastly, they're less precise than benchtop models. So there's some serious drawbacks about them, even though they can produce a lot of data quick. So the goal of this project is to look at how accurate and precise are portable X-ray fluorescence measurements. Do soil components, which is things like organic matter, moisture, rocks, affect the accuracy and precision of portable X-ray fluorescence? Because oftentimes we don't have the ideal conditions, which are, homogeneous soils that have nice flat surfaces for analysis and are dry to the bone. So oftentimes they have rocks or cobbles or stones or gravel. They can have high organic matter content, 30% or more. And then oftentimes they are wet. They have field moisture conditions, and you don't have the ability to dry them in the field. So under phase one of the project was to conduct some laboratory experiments to see how does moisture, rocks, and organic matter affect our perceived measurements of elements. So first off, Eric Sirkovich and Sandra Walser collected some urban forest soils in Massachusetts, Vermont, Connecticut, and New York. Then we brought them in the lab for analysis. So we manipulated several conditions to see how do they affect the perceived metal concentrations in the sample. So we altered the percent organic matter by adding coffee and sugar, no creamer though. We altered the moisture content by adding water and then drying so we can control the moisture content, and then also adding glass beads. And the glass beads are there to act as stones or small stones which can potentially get in the way of the beam and absorb or deflect the radiation. So we measured the concentrations of several elements, potentially toxic elements, using the Hitachi portable X-ray fluorescence and the SciAps portable X-ray fluorescence. And then we use a traditional method to assess trace elements in soils using a strong acid digestion. An important note is that this does not use hydrofluoric acid, so it doesn't get total concentrations, but it gets pseudo-total concentrations, which is everything that's not within a a crystalline silicate phase. And it was measured using an Agilent ICP-MS, and then also for higher concentration elements, we have an Agilent ICP optical emission spectrometer, OES. So first off, looking at the Hitachi and SciAps comparisons for their portable X-ray fluorescence measurements with the ICP-MS measurements, we can see that copper was not on the 1-to-1 line, which is shown there in gray. Zinc was closer to the 1-to-1 line, and then lead was also close to the 1-to-1 line, but still off. So that shows that there was a significant underestimation of copper by the ICP-MS measurements and lower measurements for ICP-MS for zinc and lead. That's again because we don't do total digestions, we're using strong acid digestions. So it's nothing too different or unexpected. But what's interesting here is that zinc and lead, they do agree between the two instruments for Hitachi and the SciAps, but we could see that we had lower perceived concentrations for copper using the Hitachi portable X-ray fluorescence. And again, the ICP-MS underestimated copper, lead, and zinc because we did not do a total digestion. All right, now moving on where we actually manipulated moisture content, the x-axis is the percent moisture, and on the y-axis we're looking at the measured divided by a theoretical subtracted by 1. So this is basically a percent difference from the true value measured under normal conditions, which is without additional moisture, without organic matter added, without silicate beads. We can see that we have a slight positive trend for copper, lead, and zinc with increasing moisture. We have decreasing perceived concentrations with organic matter, and then we also have decreasing perceived concentrations with silicate beads. So overall, it shows that moisture led to overestimation of 20%, while glass beads and organic matter led to 20 to 40% underestimation of copper, lead, and zinc concentrations. Next, we did a field application where undergraduate Eric Sirkovich, for his undergraduate thesis, and we went to 460 sites across Springfield, Massachusetts, Lexington, Massachusetts, and Hartford, Connecticut. Eric processed the samples by drying them and then sieving them, and then also doing loss ignition. And he measured the soils 4 times under field moisture, dried, sieved, and loss ignition conditions to see how do they change the perceived concentrations. So first, looking at an example of lead, we can see that lead has a very close relationship for 1-to-1 line. So that means that the ICP-MS concentrations, which are on the x-axis now, strongly agree with the PXRF measurements for lead on the y-axis. So that's really good. But our R-squared is 0.88, which is still really good, but not as good as the 0.95 when we actually dried them in the oven. But note that after we dried them, we then have an increase in perceived PXRF concentrations by about 35% overall. Similarly, with the after sieving, we still have an overestimation. And then if you do loss ignition, we still have a significant overestimation. So again, the unprocessed soils actually had a better fit, but a little bit more scatter or lower accuracy. And lower precision, higher accuracy, lower precision. But the drying and sieving led to an overestimation of about 30%, and loss ignition increased that to 40%. So it looks like processing can actually then increase your perceived concentrations beyond what would be measured through traditional methods. Now, looking at a different element, looking at cadmium, for example, we can see that the relationships are very poor. And that's because portable X-ray fluorescence really struggles at the lower end of less than, say, 5 milligrams per kilogram concentrations of most elements. So here, this is where the traditional methods are quite important. So you can actually get a number from the instrument, but it's not accurate nor precise. So you have to know the limitations of the methods that you're using in the instrumentation. All right, and then lastly, we have a third phase, which is still going on, which are developing the protocols to ensure accuracy and precision for soils, and then trying to understand the application for urban gardens, because those are places where you can potentially have uptake of toxic metals into plants that can negatively impact humans. So this is still a work in progress, but we were looking at 10 community gardens across largely the Northeast, although we have one site in Missouri. And we were looking at now nutrients as well. We are also assessing toxic elements, but these graphs to the right are looking at calcium, potassium, and phosphorus. And we're looking at different conditions, wet, dry, sieved, which is the field moisture content, and then also different measurement parameters in the instrument, which is 2 different modes, A mode that we built and S mode, which is a built-in mode. We can see that we have lots of variability in the perceived concentration of calcium, potassium, and phosphorus. Now we're working to see if we can make predictive models about how much of this calcium, potassium, phosphorus is actually available for plants to take up using only the PXRF measurements and organic matter and pH content of the soil. So we're still trying to develop that and see if we can make those models to have accuracy and precision to say what is plant available for in urban gardens. So with that, I'd just like to conclude I'm very thankful for the USDA NRCS for providing the funding through the Soil Science Collaborative Research Program. The PXRF, provides a very quick snapshot of metals and soils. Depending on the instrument, it may or may not be great. So you need to definitely validate using traditional methods. Drying and sieving do not appear to improve the accuracy overall, but this could be soil specific. And then lastly, total elemental concentrations are useful, but linking them to plant uptake and ecotoxicology needs further development. So with that, I'd like to say thank you and have a good day.